So it's a pleasure to have with us Professor Rafal Demkowicz-Dobrzanski. Maybe I have not properly. So Rafal is a faculty member in the Faculty of Physics, University of Warsaw, Poland. He's quite well known for his works in quantum metrology, quantum information theory in general, and in metrology. Those are also his research interests. So Rafal did his PhD in 2004, thereafter got habilitation in 2014. So he was a research assistant at the Center for Theoretical Physics, Polish Academy of Science, Warsaw, during 2003 to 2007. Thereafter, from 2007 to 2009, he was assistant professor at the Institute of Physics, Nicolaus Copernicus University, Torun in Poland. From 2010 to 2017, he was assistant professor in the Faculty of Physics, University of Warsaw. And from 2017 onwards, he has been associate professor there in the Faculty of Physics, University of Warsaw. He is, as I said, in the field of quantum metrology, he is a pioneering figure. So today we'll listen to his talk about quantum technologies AD 2022. Rafal, you can start.
Okay, thanks a lot for the introduction. It's very nice talking to you. So yes, I'm working on quantum metrology, but this talk is supposed to be more general. So I would give you three tastes of quantum technologies, and I will finish indeed with quantum metrology as the final taste. But before I go to my talk, I should mention to this year's Nobel Prize, because it's the first Nobel Prize where quantum information is mentioned explicitly. So the related Nobel Prize that was awarded in 2012 for David Wineland and Serge Haroche was, I would say, more for manipulation of atoms, so more for, I would say, quantum optics. And this year, Nobel Prize is mainly for experimental violation of Bell inequalities, but as you can see also in the announcement, there's quantum information science is mentioned, and this is mainly due to, the contributions of Anton Zeilinger, who is one of the awarded scientists. Okay, so going back to the talk, I would like just to start with the visions. So you are probably aware of the very old visions of Richard Feynman, which somehow laid ground for our present-day quantum technologies. So basically, these are the famous quotes that there is plenty of room at the bottom, already in 1959. And a bit later, his quote, which basically describes the operation of quantum computer. So we can, in principle, make a computing device in which the numbers are represented by a row of atoms, with each atom in either of two states. The ones move around, zeros move around. Finally, along a particular atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant. So these are, apart from visions, we have a lot of work done and also a lot of money invested. And I would say that the last couple of years, we've seen a huge increase in investment. So I think that this is a defining moment indeed for quantum. In 2018, EU launched this quantum flagship program with very ambitious long-term goals. So including universal quantum computer, quantum sensors devices integrated within mobile phones, quantum internet. So, okay, these goals, I would say they are very ambitious and probably will not be achieved, but some progress in this direction definitely will be made. So even maybe this is not a characteristic feature of Donald Trump presidency, but actually he also contributed something to the development of quantum technologies in US. There is, of course, Indian program and of course Chinese program, which is basically 10 times larger in money compared to the others. And of course, there are a lot of private companies involved, like Google, IBM, Toshiba, Huawei, NTT, and a few others that try to be on this top of technological development. Okay, so to make things a bit more systematic, I want to strengthen this fact that we usually divide quantum technologies into these three pillars: quantum computing, quantum communication, and quantum metrology. And in this talk, I would just want to focus on one achievement in each of these pillars, because I mean, there's a lot of work and a lot of achievements and so on, but somehow there are a few that are really, I would say, unique and original. Many of them are just repeat. I would just want to focus on one example in quantum computing, quantum communication, and quantum metrology. By the way, if you find something that you want to ask about, please do interrupt me. Maybe you want to interrupt me now. Yeah, so if not, then I will go on. The basis of quantum computing is the qubit, that we can have a superposition of two levels in an atom, for example. And the essential advantage coming from this fact is the so-called quantum parallelism. So basically, since we can make a superposition of zeros and ones, if we have n qubits, we can basically make a superposition of n bit numbers. So writing this not very formally, we can just say that we have like exponential superposition of all 2 to n numbers. And if a quantum circuit, logical circuit, is given, we can just send this quantum state through this circuit, and by linearity of quantum mechanics, in a single run, in some sense, we compute, we perform calculations for all the input data. So for like exponential number of instances of this data. Obviously, there is this issue that we cannot read out all the results at once. So it's not clear whether there is indeed a practical advantage at all. I think will be maybe awarded a Nobel Prize in a couple of years for something again related with quantum technologies and information, because this was his genius idea how to make something of this quantum parallelism. So maybe you are aware of this algorithm. So this is the simplest quantum algorithm possible to imagine. So the goal is just that we have a 1-bit function, and we have to decide whether it's constant function, so f of 0, and or not constant function. And classically, we need to compute this function 2 times. But if we implement this function in a quantum box, in a kind of unitary that just multiplies our qubit vector by -1 or 1, depending on the value of this function, then sending a superposition of zeros and ones, and we will see that depending on this, we will either have a vector which is 0 plus 1 and some global sign which is not really relevant, or a function or a state 0 minus 1, so an orthogonal state. And between orthogonal states we can distinguish, and that's why deterministically get the answer in a one go. Okay? So this is this simplest example. And now everything that's done in quantum computing algorithm is actions of this kind of, I mean, basically almost everything is a variation on this. For quantum computer scientists, quantum computing scientists, they usually like to plot this kind of X. So this X represents the complexity classes of certain computational problems. And the quantum computation class is something that contains problems which may be for classical computers, maybe the so-called NP class. So a class which is requires polynomial amount of computation to check the result, but not necessary to find the result. Okay, and this BQP is called formally bounded quantum bounded error quantum polynomial time, is the class, computation class that is offered by quantum computers. And of course, nothing is certain in complexity theory, so that's why everywhere there are question marks. So it's hard to say whether there are really problems that can be done more efficiently using quantum computers than classical computers in general. So the Shor algorithm for factoring, we know that it is basically almost exponentially faster than any known classical algorithm, but it is not proven that there is no classical factoring algorithm performing as fast as Shor algorithm. So this Deutsch algorithm is the first one. The Shor algorithm, I would say, is the most famous one because it's also a very practical one in the sense that it's very important from the point of view of security. Because once we can factor large number internet communication that is encrypted using public key encryption, and this is almost all the communication we are doing on the internet. There are many other algorithms. If you are interested, there is this webpage, Quantum Algorithm Zoo. There are hundreds of algorithms, but this doesn't mean that all of them are very interesting or useful, because some of them will just have a small quantum advantage. While to really think of a quantum algorithm to be useful, we should have something which is really a significant advantage, at least on this theoretical level, because when we try to implement it in practice, we will experience so much troubles that, for sure, this advantage will go down. So we should start with some really strong advantage to really see it in practice. Okay, so how we want to build a quantum computer? So there are many physical platforms. The one that is, I would say, most clean and elegant is this ion traps platforms, where we really address individual qubits in the form of ions in a trap, and it achieves the longest coherence times. So that's why I say it's the most clean one. But it's limited in the number of ions that we can operate on, and there are records that can go up to maybe 30 qubits there. We have this platform which is like purely photonic platform, where we try to just use photons and interference in integrated optical circuits. And this is also very elegant, nice platform, because photons are also very they preserve coherences very well, but the problem here is it's very difficult to produce individual photons on demand, and also to control losses in the system. So there's also a lot of work in this direction, and there is also even this company PsiQuantum, which is really promising a lot, but I'm not sure how much of these promises will be realized. And the most popular platform for quantum computing nowadays is this superconducting qubit platform. And basically, almost all the news you hear in recent years are the news related with superconducting qubits, processors based on superconducting qubits. So the records now are like over 100 qubits for in a universal architecture, in the sense that you can operate, basically perform arbitrary gates on these qubits. I should mention that there is some, I would say, alternative route being developed, which is mainly represented by this company D-Wave, which is following this approach of so-called adiabatic quantum computing, which is not using the quantum gates architecture, but rather the quantum adiabatic theorem to find the ground state of some system, which gives us the solution. And this is, I would say, very messy. Yes, The question is there some question? No. Okay, it's a bit messy platform because it's very hard on this platform to really predict whether we can expect quantum speed up there. We get some results, but it's very hard to say how long we have to wait with the computation to have a credible result. Okay, focus on this main news, which was the highlight in 2000. Yes, I see some voices. I don't know if there is some question or. I don't know. Okay, or maybe I hear myself.
There is no question till now. I mean,
okay.
If it's some question we can ask.
Okay.
Yes. No.
So surely many of you have heard this news in 2019 about Google result where they claimed that for the first time they achieved this quantum advantage with this Sycamore processor. So they claimed that they performed a computation in 200 seconds, where classical supercomputer it would take 10,000 years. So it's important to realize what kind of computation is being done on these platforms, and also in the more recent experiments that were done. So basically, these are the algorithms that we can have hope to be able to show that we do something better than classical computers. And unfortunately, these are very boring algorithms. In case of Google experiment, it was just performing a random quantum circuit. Okay, so just imagine you have some set of gates and you choose randomly these gates, and this is some kind of a random quantum computation. And you can prove that simulating such a random quantum network is difficult classically. Okay, so that was the purpose of the scheme, that there were theoretical arguments with which you could strongly argue that this is a difficult classical computational task, which is not very common to be able to show, as I mentioned before. And with this problem, the simple goal was just the quantum computer obtained in the end the statistics of our qubits, measured qubits, and the goal for classical computer would be to simulate this probability distribution. Yes, so to be able to provide the same sampling of results as this quantum network. So actually, in this case, the Google achievement was, I would say, on the verge of showing this quantum advantage, because IBM claimed at that time that they would be able to perform this computation in 2 days, not in 10,000 years. So maybe Google was a bit over optimistic about their claims, because they didn't appreciate enough the memory capacity the present classical supercomputers have, which are of the order of petabytes. So what is our situation now? So we are in the so-called noisy intermediate scale quantum computing era, which was a term coined by John Preskill, which means that we are operating on devices where we have, okay, substantial number of qubits, but they are not good enough for our purposes. So errors are still too large to really be able to implement the so-called quantum error correction and scale things up. So we have to stay with these hundreds of qubits and live with this noise we have, and just try to find some useful tasks, or maybe even not useful tasks, in which you can demonstrate some quantum advantage. Okay, so for this Google experiment, it was just the goal of sampling some probability distribution, which is difficult to sample classically. And if you look deeper into what this quantum processor really did, mostly it produced noise. Okay, so if you wanted really to plot the probability distribution of the samples, it would be like less than 1% weight for the true sample probability you wanted to get. And this was put on like a flat background noise, which was like 99.8% weight. So this should show you what was the level of noise in this system. Like the noise was 99.8%. Okay, 99.8% of the data obtained was just rubbish. That's what happens when you have uncontrolled noise, which you don't correct, and it propagates in the system. So if we now want to really do serious things, we need to implement the so-called quantum error correcting codes, for which we need to have our computing elements good enough. So below the so-called fault tolerant regime, which is errors of orders 10 to minus 4 and not 10 to minus 3. So like at least order of magnitude improvement in this elementary components. So this is not unimaginable. I hope we will achieve it in a couple of years, but still we have something to do. So just to mention the latest developments, so this kind of experiment as Google did was repeated on a larger scale in China with 60 qubits. So in this case, you could really say that it's not possible to simulate it classically, even with this IBM supercomputer. The other experiments that people are sometimes performing, which again can be shown to be difficult to do classically, is the so-called boson sampling problem, which is again not an interesting problem in itself. It's just a problem designed to demonstrate quantum advantage. So these are the efforts where we try to just scale up systems without maybe taking so much care about the quality of the elements. The other approach, which I think is maybe more perspective, okay, with better perspectives, is really trying to increase the quality of elementary elements. So for example, try to really push this error correcting approach to maybe have less number of qubits, but with better quality that we are able to correct. So this is being done now, and I think we are now on this really the moment that people are able to keep the logical qubit, at least one, for a very long time, maybe even without any serious limitation. Okay, so this was this quantum computing part. Now, going to quantum communication, I should be maybe more brief with this. So basically what I want to talk is about quantum cryptography. So we believe in this security of our internet communication because we believe factoring is hard. And we use this RSA protocol where the main player distributes two large prime numbers, I mean a product of these two large prime numbers as a public key. And it's difficult to factor this. So you can encode information without knowing the factors, but to decode, you need the factors. Okay, and that's why we have the security, and we are using it every day. Okay, so the problem here is how to be really sure about the security, because we believe in this fact that factoring problem is hard, but on one hand we have no proof of it. On the other hand, we have quantum Shor algorithm, which actually shows that it's not secure. But okay, we believe that nobody has a quantum computer in their cellars and cracking codes. So fortunately, there is this provably secure cryptographic method, which is called one-time pad, which is just the method where two parties share the secret random key of the same length as the message. And it's very easy to prove that if we have such a random key that are private and the same length as the message, we can just do binary addition bit by bit, and we have a completely secure cipher. Okay, and to decode, we again do binary addition and we decode information. So here the problem is just how to distribute the key. Okay, because we need very long keys. So of course you can distribute it on paper in some secure way. And this is also being done in some very sensitive cases. But we have this alternative, which is the quantum key distribution. And I think that it will also be awarded at some point a Nobel Prize to Bennett and Brassard for this. So basically the idea is that we use non-orthogonal quantum states. So usually we describe it using polarization, that we have like horizontal, vertical polarization, but we can also have arbitrary polarization, which produces a non-orthogonal state, which cannot be distinguished perfectly from other non-orthogonal states. and we perform measurements with polarizers. And this is all we need. So the BB84, which I guess you all are familiar with, is that we have this quantum channel where we send the photons, and we have this classical communication channel where we will agree on the results we have, which is publicly accessible. So we send this randomly 4 types of states with polarization, horizontal, vertical, and diagonal and anti-diagonal. And we assign these bit values to these states. The receiver, on the other hand, randomly chooses one of 2 bases, either vertical, horizontal, or diagonal, anti-diagonal. And in the end, if the receiver measures in a compatible basis with the basis that was used by the sender, she should get the correct result. And if the basis is incompatible, the result will be random. So after the transmission, they use this classical communication channel to throw away the instances where they expect the results to be random. And on the other part of the bits that they receive, they check part of them, just a small sample, to see what is the level of disturbance in this supposedly correct bits. Okay, and this level of disturbance allows them to tell how much information might have leaked about the states. And because non-orthogonal states cannot be distinguished perfectly, we know that nobody could learn all the information about the states. And moreover, if they learned something, they needed to leave the disturbance there. So we can assess it, and we can state the conditions for in the end. Okay. The main challenge in these experiments is very weak optical pulses. I mean, ideally we should use single photons, but in practice it is not the best way to go. People would usually use like weak coherent pulses, and this in some sense opens some risks for attacks, but there are protocols to counter this, so-called decoy protocol. So usually in practice, people would use coherent pulses, but still they are weak pulses, which means that this weak pulse should go through the fiber, and there should be some non-zero probability that this photons that at least one photon survives. So this basically limits our communication via fibers, because the best fibers have this loss ratio of 0.2 dB per kilometers at infrared range. So this means that if we, for example, use 400 kilometers fiber, we have probability of getting a photon at the output 10 to minus 8, which looks very bad, but okay, it is still not hopeless, because we can have a repetition rate like gigahertz. So we would be getting like 10 photons per second. Okay, so okay, this will be a slow communication, but for very sensitive data, maybe it's worth trying. So indeed, the records via fibers are on the order of 400 kilometers, I would say. And I don't see the possibility to go much beyond this, except for the using of so-called quantum repeaters, which is the way somehow to avoid this problem of loss growing exponentially with the length. But there is also other option, communication in free space. So basically the main idea is to communicate via satellite. It would seem much more challenging than the fiber, but on the other hand, if you realize how thin is the atmosphere, that it is just 10 kilometers, basically, okay, the atmosphere when it's really optically dense is just maybe 10 kilometers wide, then the total loss is not as high as in, for example, 400 kilometer fiber. There is an issue with diffraction of the beam, which makes it a slightly challenging, but it's still better in terms of overall transmission than the fiber for the long distances. So now you can communicate over 1,000 kilometers with the satellite, and the communication will have higher rate than the fiber of this length. Okay, And actually here we should mention our Nobel Prize winner, because one of these experiments of distributing key between Austria and China was done by Anton Zeilinger and by Austrian group of Anton Zeilinger and the Chinese group. Okay, so also in relation to this year's Nobel Prize, it's worth mentioning that we have this entanglement-based key distribution, quantum key distribution protocols. So the most famous is this Arthur Eckert protocol from 1991, where basically instead of sending single photons, we are using entangled pairs of photons. And okay, the protocol itself goes very similarly, apart from this fact that in the end, it's very beautiful that we can somehow connect the security of this protocol with actual non-existence of local hidden variables. So somehow, if the world was classical at its bottom, we would not be secure about this. We could not design a secure quantum communication protocol. While if we really believe that quantum mechanics is fundamental, then actually the security of this protocol may be related with violation of Bell inequalities, which is exactly the theme of this year's Nobel Prize. And also the experiment was performed for distributing the entanglement to two stations separated by 1,200 kilometers. But in this case, as you can see, the rate was just one pair of entangled photons per second, and it was not enough to have enough statistic to really generate secure key. But for distributing entanglement, it was fine, and violating Bell inequalities, it was sufficient. Okay, so now I want to move to this last part, which is the closest to my heart. So I would like to tell you briefly about quantum metrology, or at least the main achievement of quantum metrology. So if you want to say what is quantum metrology in one sentence, I would say that this is the goal of manipulating individual quantum systems to make the most of quantum coherence and entanglement in order to boost measurement precision. So depending on the physical systems you are thinking of, quantum metrology can have very different phases. So optical interferometry is basically what comes first probably to mind when we are talking about quantum metrology. So standard interferometer, of course, uses quantum coherence, okay? Because interference is basically quantum coherence of photons. But still, since we were doing it from the 19th century, we are regarding this kind of scheme as classical. So where if you are using classical light, so I would say coherent states, okay, formally. So even though it's still very quantum because we are using quantum coherence of photons, we call it classical. Okay, but you can boost this interferometry by using non-classical states of light, involving entanglement between photons, or using a bit different description, you can say that we can benefit from using the so-called squeezed state of light. Okay, and then the main problem with these quantum enhanced schemes, if we want to do them in practice, is the photon loss. And then you have other platforms with atomic interferometers that are, for example, used in atomic clocks. And then again, you can try to boost this, let's say, more basic schemes, which just utilize coherence. You can boost it to a more sensitive devices by additionally, for example, entangling atoms together. So using not only coherence of atomic states, but also entanglement between atoms. Okay, so this is like the next level of quantum, let's say. And similarly, in solid-state devices like NV centers, which can be used to sense magnetic fields, you can try just to use the levels of these sensors and coherence between them, or you can try to entangle these NV centers to some nuclear spins around and play more tricky stuff. Okay, so I give this table to show you that quantum metrology uses coherence and then tries to go even further, okay, to boost it, to exploit entanglement as well. And of course, this is much more challenging, and usually the decoherence is the factor that limits this advantage a lot. So today, I just want to focus on this optical interferometry example, because it's the simplest, and on the other hand, is the most spectacular in its achievements. So just recall like a classical Mach-Zehnder interferometer, and if you set a coherent state and it's split and there is a relative phase between the two arms, okay, you will have some interference, and in the end, you will obtain some number of photons registered in one detector and the other, and on average, you would have just a standard interference fringes. Okay, so you can plot this average expected number of photons as this cosine function. And if you register some number of photons, then you can estimate what is the phase, okay, what is the relative phase. And actually, you can prove that the best estimator is just this, I would say, most intuitive estimator, that you just invert this relation between the expectation values and the phi. So you take the arc cosine. But because you have coherent states here, the detection number of photons detected follows the Poissonian statistics. Okay? So we have fluctuations in detected number of photons, even if the phase is kept constant. That means that from shot to shot, you will estimate a bit different phase. And this is this gray area that is depicted here. So in the end, you will have the shot noise scale. So 1 over square root of the number of photons you are using. So the more photons you are using, the better is the estimation precision, but you are limited by this 1 over square root of n. And now the question is, can you beat this scale? Okay? Can you beat this precision of estimating this distance between the paths better than 1 over square root of n? So notice that if lambda is the wavelength of our light, with strong light beams, we can estimate the difference with the precision order lambda over square root of n. So this is very important, that wavelength is not itself a limit to the precision with which we can estimate the difference of these paths. Okay, of course, it enters the formula, but if you have very strong light, we can estimate distances much better than the wavelength. This is something that usually people are puzzled when there are this news about quantum gravitational wave detectors, and they say that we estimate the distance between the mirrors with the fraction of the size of the atom, yes, or even the nucleus. Okay, so it's much shorter than the wavelength of light we are using. Indeed, but it's not so absurd, okay, because we are much more sensitive than just going from one maximum to the other maximum of the fringe. If we have strong beam, we can locate ourselves very well at some place of the fringe with very high precision. Okay, but this was somehow classical still. And in 1980s, there was this great idea by Carl Caves that instead of sending vacuum to the other input port, so just doing nothing, we can send the so-called squeeze state of light to the other input port of this Mach-Zehnder interferometer. So formally in the phase space, squeezed states of light are described as this ellipsoid instead of circles, which are representing coherent states. This basically means that we have, for example, lower fluctuations of electric field, but larger fluctuations of magnetic field. Okay? Whereas in coherent states, we have them like more or less the same. I mean the same up to the some kind of natural scale we are using. And if you do it, actually you can show in this setup that the fluctuations of detected number of atoms become sub-Poissonian. Okay? So there are lower fluctuations. And if there are lower fluctuations, there is lower uncertainty in estimating phase 5. Okay. And actually, even though it's not clear from this picture, squeezing, if you look, because this is like a mode picture. You have mode, one mode, second mode. In one mode, you have coherent state. In the other mode, you have squeezed state. But you can also look at this problem in let's say, like first quantization picture. So like in a particle picture, in terms of photons, which are like separate particles in some sense. And then you will see that there is entanglement in this state. And so you can look at this problem of employing squeezed states of light as, in some sense, exploiting entanglement between photons. And actually, you can show that in ideal world, you would be able to obtain precision lambda over not square root of n, but n. And this is so-called the Heisenberg scaling of precision. And amazingly, this idea works. And from 2019, the main gravitational wave detectors now operate using the squeezed states of light being sent to this other input port. And unlike quantum computing or quantum communication experiments, which are mostly like proof of principle experiments, which are not really performing anything very useful, but just demonstrating that something is possible, here, the squeezed states of light are used now in a regular operation of these devices. And they actually lower the observable noise. So these are the plots of this noise you observe in gravitational wave detectors depending on the frequency of the signal you want to detect. So without going into details, I can just tell you that this green curve represents noise when you use squeezing, and this black curve represents noise when you don't use squeezing. Okay, but apart from this, this is like the same device, and it's amazing that I don't know if you see this. I don't know if you see this line. Okay, but okay. The important thing is that this noise is reduced by 35%, which, okay, you may say, okay, it's not very much, it's just a little. But you should appreciate it, because to get this reduction, we are just using very few photons being sent as this squeezed vacuum state. Very few. So like, this is completely uncomparable. You are using like maybe 10 to, I don't know, 20 photons per second in this main laser beam, and you are sending maybe 100 photons per second in this squeezed beam. So if instead you wanted to obtain the same increase of precision just by boosting the laser power of your main beam, you would need to increase this power by 85%. Okay? So almost double this power. So of course, this would be much more difficult for the setup, because it will have other effects like heating things, instabilities, and so on. While here, you basically do nothing. You just send, okay, a few photons, but cleverly prepared, and you get the same advantage. Okay, so if you want to be very like flashy, you can say that like 100 quantum photons does the same job as the 10 to 20 like classical photons. So I think that this is a great achievement. So that's why I would say that this is real example of where we benefit from quantum entanglement. Okay, you may argue it's not a practical achievement in the sense not for everyday life. It's not useful in everyday life because it's detection of gravitational wave, which is not of much interest to common people. But still, it's a practical achievement. So we really improve the precision of our devices, measurement devices. Okay, so to astronomers, you should say that thanks to squeezing, you can increase the number of binary neutral star merger detection by 50%. This would be more or less correct statement. Okay, so I would stop here, and I will just leave you with these 3 pillars and these 3 examples. And I'm looking forward to the next Nobel Prize. Maybe not next year, but maybe in 3-4 years, I guess there should be a Nobel Prize in quantum technologies, appreciating the work done both in theory and the experiment, because this year Nobel Prize was just for experiments. Okay? I think that there are people like Charles Bennett or Peter Shor, which really deserve the prize for the theory. And I really look forward in the coming years. And I also look forward to your questions. Thank you.
Yeah.
Okay,
so again, for such a nice talk. Yeah, you can start answering the question in the chat box. Yes.
Yeah. Okay, so in classical communication through fibers, how we deal with loss? We deal with loss in a way that we put amplifiers on the way. Okay, so if our impulse, our optical pulse gets amplified from time to time, and that's fine in classical world, but in quantum world we know we have the so-called no-cloning theorem. So we cannot just amplify non-orthogonal states, which you use in cryptography. We can amplify orthogonal states, but for cryptography we need to use non-orthogonal states. So that's why amplification as a way to increase the distance of the quantum key distribution is not a way to go. But there's another trick that maybe instead of amplifying, we can like teleport our state on shorter distances, and it may be in the end much more efficient than sending a single photon, because a single photon, to go through a very long way, it has to survive all the way on its own. While if we do teleporting, we can first distribute entangled pairs on some smaller distances, and we can repeat it until we are successful. And only when we are successful, we are teleporting the information that comes from one side. And in this way, we have much less impact of loss with the increasing distance. Still it is, but it will be not exponential. It will be just a polynomial.
Yeah.
Okay.
I have one question. What is the status of error correction in the practical computation? And related to this question, whatever the recent simulations of other things like topological spin liquids are topological materials which is being carried out in like due to so much of noise. So is this a real simulation or whatever? I just want to hear you.
Okay, so concern correction stuff, as I mentioned, we are at the place now where we really can implement some quantum error correcting code to protect like a single logical qubit. And in some sense, we can keep this coherence in this single qubit for very long times. But of course, we would like to have like many logical qubits which we can protect by error correction. This is still not achieved. Concerning this, I would say solid state questions and quantum simulations, I'm not an expert in condensed matter theory, so I would not tell you much. I think interesting. I would just I have to leave you with this question unanswered.
No, because of so much of noise, which as you rightly pointed out with the Google's experiment, it's so much of noise. Any of these simulations is it really meaningful?
Okay. Yeah. So of course that's the problem, and as I say, I'm not. You should have some kind of benchmarks, yes, to be able to say whether you are performing with enough precision to have your results really meaningful. And this really, I don't know. I think it's very tricky. Especially what I mentioned was this D-wave computing device, which is an explicit example of this situation. You have noise, which basically tells you that coherence is gone much earlier than your computation time. So there is no way you can keep coherence during your whole experiment. And still, some people would claim that you have some quantum advantage there, which is very suspicious. Yeah? So you may have some advantage, maybe it's not really quantum, maybe it's just because the design is in some sense nice and it's better than standard classical designs. But to have really the argument that you control computation and you know what's going out of it, so you need to have control over the errors, or you need to have some good benchmarks which you check for small scale systems, and then you try to extrapolate it and believe that for larger scale it still performs well. So for example, if you want to perform simulation with some quantum noisy, let's say quantum noisy computer, you first perform it on a very small scale, few nodes, and simulate few atoms, which you can also compute rigorously on a classical computer. Okay, and then you see whether it agrees. Then you can say, okay, my errors are sufficiently low that I see, at least for a small scale system, that it agrees. So I expect that it extrapolate, I can believe in this result a bit more, but still, okay, which means like million physical qubits probably. So it's extremely distant. So I think we need to look for other applications like smaller scale stuff.
Right. Okay. Okay. And what about, so you mentioned at least 3 platforms like ion trap, one is photonic one, and other one is the superconducting qubits. So
yes.
what is the most promising one in terms of scalability? I mean, like, is there any advantage over one to another, like in terms of scalability?
Yeah. Okay. So of course, the superconducting qubits seems to be the most scalable now, at least up to these hundreds of qubits that they go. Ion trap seems to be least scalable, but of course there are these ideas of ion trap in the chips where you can move ions around from one, room to another room, and in this way go around it. With these photonic qubits, on the one hand, it's very easy to make a lot of optical elements integrated. And on the other hand, it's very difficult to have these photons on demand in the numbers you want. So, okay, at the moment, I think the superconducting qubits are the most promising, but still, they also have their limitations. So it's hard.
I see. Thanks. So I have last one more question. So it's like about quantum communication. So you said about the cryptographic protocol, and most of our daily use is based on RSA protocol, which is basically on factoring, right? So why don't we design classical algorithm itself, which is NP hard, and then based on that we can maintain our secrecy or privacy itself, because even quantum computer cannot solve the NP hard problem, like in polynomial time.
I mean, they're NP complete, I think.
Yeah, complete. Sorry. Yeah.
Okay. Yes, but you know that there are no proofs that any algorithm is NP complete. So. Okay. So the computational complexity theory is so bad in proving that something is NP complete that we have no guarantees. That's the problem. But of course, if we had such a proof, then probably it would be enough. I mean, if we have like that's no classical algorithm can beat it, then maybe we should not be worried even about quantum computers until they are very big. So then we would be fine. But now it's really a risk that if this factoring algorithm, classical factor algorithm is found, which would be much better than the present one, it's a huge risk.
I see. Thanks.
Hi, Rafal. Thanks for the nice talk. So I just had a very naive question. So you mentioned about using quantum. There are a lot of these quantum computers available for testing codes and all. So till now, what is the best possible problems in physics that has been already tested using quantum algorithms or quantum computers?
But I mean, of course, people are doing these quantum simulations, simulating some condensed matter systems, but all other applications I know, they have not shown anything useful that cannot be reproduced on classical computer. Yeah? So if you are asking for something that we really used quantum computer for something that could not be done on classical one, then I would say we don't have such example.
Okay, and right now the main number of bits that can be simulated is 64 maximum, or is there?
I mean, with these superconducting qubits, you have like 120 IBM processor. But
Okay.
of course, you know, it's not about the number, because you can increase this number still, but it's about the quality of these qubits. Yes, I mean, it would be much better to have 30 qubits with higher quality than these hundreds with lower quality, because then the noise will propagate so much that, as in this Google experiment or any other with this kind of devices, the noise will very soon be predominant, because you know, you need to apply gates in a sequence, and if you apply gates in a sequence, this noise will grow exponentially, because you only get correct result if no error happened on the way.
Yeah.
In neither step, in no step. So this is exponentially, the probability goes down exponentially.
And there was some discussion about this topological quantum computing, like using topological states, because they are already protected. They don't get destroyed. But what is the status of those? Like, is it?
So, okay, so there are this topological error correcting codes approach. And the one I mentioned with the 17 physical qubits with superconducting systems, I think was along this line. So I would say that now with this topological approach, we can try to, for example, protect one logical qubit. Okay?
Yeah.
So yeah, but then it's very difficult with this topological approach to have more qubits, because you need a lot of this physical.
Okay, there were some initial discoveries about this Majorana modes in this quantum wires or something, and they were supposed to be topological. So is it those kind of research?
I don't know. I think I don't feel an expert on this.
Okay. Thank you very much.
Any other question? Okay.
Hi. So
hello.
You mentioned quantum communication, right? So suppose we spend all this money and quantum computing is not reachable for many years. Do you see that quantum communication with some limited set of things that we can control, like for example, safely securely sending some qubits and reading them out? If we know only these two things, is it still worth the investment? I mean, do you see that that has more chances of justifying the investment?
Yeah, so of course, I mean, this is a big challenge here, because many of these quantum key distribution, for example, protocols, they require like dedicated fibers, yes, and dedicated like quantum channels. And in this sense, it's very impractical. So unless we are able to connect to the standard communication network and do something via it, then I think it will still remain impractical. So now the work really goes in this direction. So I think that if we manage really to use the publicly available communication networks, which are bright, okay, so that we don't have to, say, okay, this fiber is just for us, turn off all the other communication, okay, and then we do our QKD. This is probably very impractical. But if we are able somehow to do it in a fibers that are used for some other purposes, then it would be great. But as far as I know, this is a huge challenge. But there is some other, maybe slightly less ambitious aspect of quantum communication. You can try not maybe distribute quantum key, but just maybe try to use some quantum features or some even coherence features in communication to increase the capacity of the transmission. Okay, so this is, I would say, another path which is much less ambitious, but still maybe more feasible. So maybe we can just use some phase properties and different, more subtle detectors to encode information in different way, compared to what is done now, and to benefit a bit from quantum features. And it would make sense maybe to have some gains from quantum communication. But as I say, this will be a different direction. It's not key distribution, but just capacity.
Okay, thank you. Thank you.
Any more question? So I have a name question. Do you have question? Okay, so just a minute. Yeah.
A quick question. What is the status of European quantum internet initiative, and what were actually the original goal?
So as I mentioned, this quantum flagship program, this was this big project for 10 years. So it was supposed in 10 years to have connection between a few big cities in Europe. I don't know, maybe Geneva, Paris, and I don't know. But I'm not involved in this work, so I cannot tell you what is the status now of it. And for sure, there are many nodes between the cities. Okay, even in Poland, we have like a Warsaw-Poznań connection where we do some key distribution. And in many cities in Europe, you have a connection on this distances of 200 kilometers, 300 kilometers. But I wouldn't call it internet, while it is still like, it's just node to node. And if you want to connect more than 3 parties, you basically interface it via some classical information conversion. Yes, and for real quantum internet, you really need this quantum repeaters. I think I hear myself.
Hello. Yeah, we can hear you.
Yeah, but there is some feedback loop.
Okay.
And I hear myself with the delay. Okay, but yeah. Basically yes, that's it.
Okay. So maybe this last question. So it's a name question about this. So about the achieving this Heisenberg limit in the multi-parameter estimation. So how, where are we now?
Okay, so I'm glad the question from quantum metrology. So, okay, so basically what I would say is even for single parameter estimation, it's very challenging. So first of all, we proved a few years ago that if you have noise, like for example losses in optical interferometry, then you can never reach Heisenberg limit. Okay, whatever fancy stuff you imagine. So what you can get? Okay, maybe I can share the screen again. So when I was showing to you these gains in a gravitational wave detector, okay, this is just like, a constant gain. Yes, I mean some factor. You have this gain which is 30%. Okay, and actually, what we theoretically proved for this kind of situations was that with this level of loss they have in the system, even if they could prepare some arbitrary entangled quantum states of light, like, I don't know, huge G8Z states or huge squeeze states of light and so on, they would basically not be able to improve this by maybe, okay, instead of 35%, maybe they could get to 36 or 37. So that in some sense, with this level of loss, this is the maximal gain that can be. So on one hand, maybe it's pessimistic, but on the other hand, it's also nice. So formally, we can prove that Heisenberg limit in presence of decoherence for typical noise models cannot be reached asymptotically. I mean, for large number of photons. For small, you see some kind of Heisenberg behavior, but then it somehow flattens to the standard scaling, and you can get some constant factor gain thanks to entanglement, but not more. And the nice thing is that indeed this constant factor is almost achievable in these gravitational wave detectors using squeezing. There are some tricks that sometimes you can use quantum error correction, as in quantum computing, to remove noise in quantum metrology. But this is only possible for some particular noise models.
I see.
And for example, for loss, it's not possible. If you want to do it for optical loss, you cannot do it. And this is mainly what I've been working for the last couple of years, yes, on this kind of topics. And now, if you ask about multi-parameter metrology, so the story is the same. It's even more difficult, but it's the same story.
I see. Okay. Okay. So if there is no more question, let us thank Rafal for this wonderful talk.
Thank you.